So we are going to revise the current electricity in 1 hour. What we will do is we will look into some questions topic wise. So first topic is the definition of current. So we know that average current is defined as delta Q by delta T, which is the rate of change of which is the rate of flow of charge across any cross-sectional area. And then
Yes.
you have instantaneous current as limit delta T tends to 0, delta Q by delta T. That means we have to differentiate the charge with respect to time. That will give us the instantaneous value of current at any instant. Okay?
Yes.
So one question related to this may be that there is one electron which is moving in a circular path. This is a very popular question. So one electron is there which is moving in a circular path of radius r with speed b, constant speed. So
Yes.
what is the equivalent current? Find the equivalent current.
Okay.
Yeah, try to do it. So question is, one electron is moving in a circular path of radius r with constant speed v. What is the equivalent current? Because
So will
charge
it
is flowing. Mhm.
so will it be EB by 2 pi r?
How you have done?
So time t is 2 pi r by v. So
Mhm.
your charge is E. So
Mhm.
it'll be EV by 2 pi r.
Correct. Because current is given by charge per unit time. So basically, in one time period, we can see that only one charge is flowing. That is the electronic charge E. Now here we
Yes.
have to calculate the T. T is 2 pi r by V. So answer is EV by 2 pi r. Good. Then another kind of question that you can get is where you need to do the integration. For example, if it is given that current in a particular wire is given by 2t plus 5. So it is a function of time. Now find the charge that flows through the wire in first 5 seconds. Yeah, please try to do it.
Yes.
So current is a variable here with respect to time. We have to find the charge which flows in first 5 seconds.
Yes.
So its answer will be, since I is equal to dq by dt, and here I is given by 2t plus 5. So we need to do the integration. We will do dq is equal to 2t plus 5 dt. So we have to integrate it 0 to capital Q, and it is 0 to 5. So we will get q is equal to 2t square by 2 plus 5t within the limit 0 to 5. So it will be t square plus 5t. Now plug in the values of 0 and 5. We will get 50. So it is 50 coulomb. Okay. This is one section. Next, we will discuss about the drift velocity. So next part is drift velocity. So basically drift velocity, it is the property of the uh, all the electrons which is present in a particular volume. And how can you define the drift velocity? Tell me.
Drift velocity is given by minus E into E by M into tau
Hmm.
tau AR. So drift velocity is basically the velocity with which the electrons are being pushed to the positive terminal.
Under the action of electric field, when we connect the when we complete the circuit with the help
Yes,
of the battery.
yes.
So yes, and what are the formulas that we know? So VD is equal to E. Tell me.
Capital E electric field by
By
M to
into
2.
tau. So here
Yes,
E is the electronic charge, M is the mass of the electron, capital E is the electric field, and tau
yes,
is the average relaxation time.
yes,
So we can see that here drift velocity is directly proportional to tau. So
yes,
if the relaxation time decreases, drift velocity will decrease. If relaxation time increases, drift velocity will increase. And this
yes,
gives you the reason behind that why heating of a conductor changes the drift velocity. Okay,
yes.
good.
So
There is another.
if we heat the conductor, then VD will decrease, right?
If we hit the conductor, then the electrons will move with more speed. So they
Hmm.
will have frequent collisions. That means
Yes,
the relaxation time will decrease. So drift
yes,
velocity will decrease. Correct.
yes. Okay.
And there is one more relation which involves VD. That is, it is related to current. So we will write I is equal to NEA VD. This is again
Yes,
another formula which will help us. So this is V is equal to VD is equal to E capital E tau by M, and it is I is equal to NEA VD. Here N is the number density, that is number of electrons per unit volume, and A is the cross section of that particular part that we are considering.
yes.
Good. Now, after this, let us talk about Ohm's law. We know that Ohm's law says that V is equal to IR. So R does not depend upon V and I. R depends on the dimensions and the temperature.
Yes,
Okay. And for any cylindrical resistor, we can take R as resistance of this conductor is given by rho L by A, where rho is the resistivity of this conductor material, L is the length of this conductor, and A is the area of cross section. Okay,
yes.
good. Then we have current density. So what is the relation of current density with electric field? Any idea? So current
Current
density is defined as current
I.
per unit area. Okay.
Yes.
Yes. So what is the relation between current and electric field? Current
So
density and electric field. Hmm.
yes. So I we can write as NEAVD,
Hmm.
and then the
Yes.
A will get cancelled,
Yes.
and then it'll get cancelled. So we'll be left with NEVD, and now
Hmm.
VD is given by minus E um, into E by M into 2R. 2AR. So from here we can actually get the formula that current density is equal to sigma into electric field.
Correct. And what is sigma?
It is the conductivity of the material.
Which is reciprocal of resistivity.
Yes, right. So reciprocal resistivity.
Yes. It is also known as this relation where J is equal to sigma E. This is also known as microscopic Ohm's law, whereas
Yes.
this is known as macroscopic Ohm's law. So obviously this is the default Ohm's law. Okay. But we see that in this J is equal to sigma E, how current density depends on the electric field.
Yes.
Right. Now coming to the other point, that is combination of resistors. So
Hmm.
obviously you can expect one question at least from this combination of resistors. Now in how many ways we can combine the resistors? We can combine it in series connection, or maybe parallel connection, or maybe mixed connection, mix of series and parallel. or maybe
Yes.
symmetry type of question you can get. You may also get Wheatstone bridge type of question. Wheatstone bridge, right? Or you may get infinite ladder type of question. Infinite ladder type of question. Or maybe some general arrangement. No such special name, just general arrangement. Now to do all of this, obviously series and parallel are the most basics one. And for symmetry, we can use the mirror image, that mirror concept. For Wheatstone bridge, we have to check whether it is balanced or not. For infinite ladder, you will normally get one quadratic equation which you will solve. Okay. For
Yes.
general one, you have to apply many concepts together. So let's see one question based on this. So question is, we have something like this. This is one resistor. This is another resistor. This is another resistor. This one. So this is R, 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 and R. This is AB. And this is a conducting wire like this. Now, what is the equivalent resistance between A and B? Just try to do it.
Yes.
Yeah, tell me your answer. What do you think? What will be the answer?
The answer will be R.
Okay, tell me the reason.
Because there's a connecting wire, and because of that connecting wire, the resistors will get short circuited. The potential difference also between all the points and all the points over there will be the same. So that means all the four resistors on the top will get short circuited. As a result, the current will only flow through the external wire itself. So it'll be R only.
Yes, yes, perfect. Here we can see that this potential is equal to this. This 3 point will have the same potential and this 3 point will have the same potential. So what will happen that when current will pass through it, it will bypass this and these two resistor and it will pass through this conducting wire and it will go to point B. So our equivalent resistance will be only R. So
Yes.
whenever you see any conducting wire, always try to look for any short circuiting. Okay, good. Now let us look into one question which related to ladder. So ladder type of question we can discuss like this one. This is R. Let's say this is R. This is R. You will always get a kind of symmetry of the structure. So one structure, you will see that it will be repeated throughout the entire length. So like here we can see that it is repeated like this. Now, okay, so the last one will be like this, R, and then like this one. Now how to do, let's say we have to find out the resistance between A and B. So in this scenario, we have to figure it out from the left hand side where we have A and B terminal. We have to find out minimum number of resistors, which if even if we remove, we will get the same type of pattern as we got earlier. So we can see that if we remove this R and this R, and if we connect our terminal again at A and B at this point, so we will get the same pattern.
Yes.
Now, our next step will be, instead of writing all this thing, all this thing, what we will do is, since it is similar, so we will use like this. We will write X here. And now resistance between A and B is also X. So resistance between A and B is X. This is X, but if you look into the resistance between A and B from the right hand side, we can see that this X and this capital R are in parallel, which is in series with this R. So we will get X is equal to Rx by R plus X. That is the parallel one. plus R. So we will get one quadratic equation. If we solve it, we will get one positive value of x and another negative value of x. So obviously positive value of x will be our answer.
Okay.
Okay. Yes. Now,
So,
yeah, just a minute. Yes. So now we will look into next topic, that is cells and its combinations. So cells are of two types. One is ideal cell, and another is real cell. Basically, ideal cell represents just this one. So it has EMF. So EMF means it is the maximum voltage that one cell can supply. So ideal cell will be represented just by writing its EMF. Whereas real cell has one internal resistance attached to it. So if this is the EMF, we will write internal resistance as small r. So this part, we will say that this is our cell. This complete dotted structure is the cell boundary. So within the cell boundary, we will have that EMF and the internal resistance. Now, in case of ideal cell, potential difference between the two endpoint of this cell will be same as that of the EMF. So we can write that potential difference between AB is equal to EMF of the cell. Okay, so potential difference between the two endpoint of this cell is also known as terminal potential voltage or terminal potential difference. Whereas for real cell, this terminal potential difference can be equal to E, can be more than E, can be less than E. How? That depends on what you are doing with this real cell. Whether it is being charged, discharged, whether it is in short circuit, whether it is in open circuit. So let us quickly look into that. Okay. So related to real cell, we have to remember this thing. Normally, if in the circuit only one cell is present, so that cell is usually it is discharging. That is what meant a cell is meant for. A cell is meant for discharging only. So whenever it is discharging, that means it is supplying current through it. So if this is the EMF, if we represent, this is the R, and let us let us draw the boundary of this cell, and this is supplying current through some external resistance, which is also known as load resistance. Now, the potential difference between this A and B will be represented as VAB is equal to E minus IR. So we can see that here potential difference, terminal potential difference will be less than the EMF of the cell. Reason is some potential drop is occurring at this internal resistance. Okay.
yes.
And then we can calculate the circuit current by dividing this E by R plus small r. This is the condition when cell is discharging. Now we will look into when cell is charging. So, okay.
So one second.
Yeah, just a minute. Yes.
So can you go back? Yeah.
Yeah, this one. Right. Let us look into the second condition. So second condition is when cell is discharging. So we can write like this. No, cell is charging.
Yes.
So normally when some another powerful cell is present, then the weaker cell will get charged. That too depends on the polarity. So if let's say we have this cell with internal resistance R, if this is EMF, so this is the boundary of this cell or battery. Battery is combination of cell, so we are looking at just one cell. Now, let's say there is some powerful battery involved which is supplying the current, and the polarity of the other battery, which is not our concern right now. So let's say this is E dash. So our another battery is something like this. Now it means that this powerful battery is supplying current in this direction. So if it is supplying current in this direction, that means our weaker battery or weaker cell is getting charged. So we will write down the potential difference between A and B as, so terminal potential difference between A and B is given by E plus IR. So we can see that terminal potential difference will be greater than the EMF of the cell. Okay. So you have to look into the question that whether the cell is being charged or it is being discharged. That is important to note.
Yes.
Now the next scenario is when the cell is being short circuited. So what happened that we will take the cell. So we are talking about the real cell. This is the battery. This is the cell, and EMF is E. Internal resistance is R, and we have connected this cell to itself without any load resistance. That means we are doing the short circuit. So what will happen that here also current will flow, but at once it will flow at once, and all current will be supplied. This will not repeat again. So here your current will be maximum, that is equal to I is equal to E by R. So potential difference between these 2 points A and B, potential difference between this will be E minus IR, but we know that I is E by R. So E minus E by R into small r, so R cancel, E minus E is 0. So there will be no potential difference between them. And obviously because A and B are connected by a straight wire, just one conducting wire. So they will have the same potential. So no terminal potential difference between A and B.
Got it.
Okay. Now let us look into the last scenario when we will keep the cell in open circuit. That means circuit is not closed. Okay. So let us look into the fourth scenario. Here cell is in open circuit. Cell is in open circuit. So this is the EMF R E. This is the battery outer part, just the boundary of the cell, and it is not connected to anything, and the circuit is open. So in that scenario, since current is not flowing through it, so potential difference between A and B will be same as that of the EMF. So potential difference between AB is simply E. And in fact, this is the definition that is used to define the EMF of a cell. We can say that EMF of a cell is defined as the voltage across its 2 endpoints when the cell is in open circuit. Okay. So these are some scenarios in which we can put this, we can keep the cell. Now cell combination. So cell can be combined in many ways, just like resistor. It can be in series, it can be in parallel. So let us look into some of the formulas related to that.
Yes, sir.
Okay. So combination of cells. So when cells are in series combination, now here also they may be in polarity, they may be in different polarities, same polarity, or they may be in opposite polarity. That we have to look into. For example, if we have two cells like this, we will say that these two are in same polarity. They are in series with same polarity. Whereas if we take this type of combination, so here we will say that E1 and E2 are in series, but they are in reverse polarity. So here our net EMF between these 2 points will be simply E1 plus E2, whereas here our net EMF will be E1 minus E2. If these resistors are real one, if these cells are real one, so they will have their internal resistance. they will have their internal resistance. So their internal resistance will be, since in the cells are in series, their net internal resistance will be simply plus. So here also we will have R1 plus R2. This is what it is.
Yes.
Okay. Okay. We will look into the combination of cells, the another scenario where they are connected in parallel. Here also, we have to look into the polarity, whether they are in same polarity or they are in opposite polarity. See, in the last one, we have taken only 2 cells, but the same thing can be extended to n number of cells. Here, what happens that if let's say, let us see one example. So we have one cell like this, E1, R1. It is connected in parallel to another cell. Now, this is E2 and R2. Since these two cells are pointing in same direction, so we will say that they are connected in parallel with same polarity. So here net EMF will be given by E1 by R1 plus E2 by R2 divided by 1 by R1 plus 1 by R2. And the net resistance will be given by R1 R2 by R1 plus R2. This can be extended to n number of cells. Now, if the same two cells are connected in opposite polarity, for example, one is connected like this and another is connected like this. In that scenario, only this minus sign, we will put minus sign here only. Don't write minus sign in the denominator. And also, the net resistance will not change. I repeat, if these two cells are connected in parallel with opposite polarity, means they will look like this. They will look like this. In this scenario, just you substitute plus sign with minus sign, but don't change the sign of the denominator. And also the net resistance of these two cells will remain same. This is what it is in parallel. Okay. So that is all about current electricity till now. We are left with the temperature dependency of resistance and also the Kirchhoff's law. That we will see next time. Okay.